This is the solution to written homework 10. Just like written homework 9, the instruction is to construct a concavity chart. So the first step is to consider the natural domain. Well, the log function, log of t, is defined for t is greater than 0. So, because this is log of something, this composition is only defined when that something is greater than 0. So what we need is we need x squared plus 1 to be greater than 0. So what we need is x squared to be greater than negative 1. But that's true for any x. It's true for positive x's, because if you square a positive x, that's positive. It's true for negative x's, because if you square a negative x, that will be positive. And it's true for 0, because 0 squared is 0, and that's greater than negative 1. So, the natural domain of this function is all reals. The next step is to find the first derivative. So the derivative will be 1 over x squared plus 1 multiplied by the derivative of x squared plus 1. So then simplifying a little, this will be 2x divided by x squared plus 1. Since we just computed a derivative, the first thing we need to check was whether there was a change in the domain. So the derivative is a rational function now. The numerator is always defined. The denominator is always defined. The only question is if the denominator can ever be 0. But for the same argument that we made above, the denominator can never be 0. So this expression is always defined. So there was no change in the domain. So next, we need to find the second derivative. And since f is a quotient, we'll use the quotient rule. So that's the derivative of the numerator multiplied by the denominator minus the numerator multiplied by the derivative of the denominator divided by the denominator squared. Evaluating these, this will be 2 multiplied by x squared plus 1, and then minus 2x multiplied by 2x over x squared plus 1 squared. Simplifying the numerator a little bit, this will be 2x squared plus 2 and minus 4x squared divided by x squared plus 1 squared. So that will be negative 2x squared plus 2 divided by x squared plus 1 squared. And if you factor out a negative 2, that's negative 2 x squared minus 1 x squared plus 1 squared. And so finally, the numerator factors as negative 2 x plus 1 x minus 1 over x squared plus 1 squared. So we just computed a derivative, which means the first thing we must do is check the domain. Again, this is a rational function. The numerator is always defined, the denominator is always defined, and for the same reason as before, the denominator can never be 0, so there was no change in the domain. And the next thing to check is where the second derivative is 0. But because we went through this hard work of factoring it, it's clear that the second derivative is 0 exactly when x is negative 1 or positive 1. So, on this exercise, there were several places where we could have found fence posts. So we checked here and found none because there were no breaks in the domain. We checked here and found none because there were no new breaks. We checked here and found none because there were no new breaks. And then we found these. So now we make the chart. Plot these 2 points. In each region we need to select a test point. So how about negative 2 for that one, 0 for that one, and 2 for that one. So evaluating at each point, so that's negative. Plugging in negative 2, that one is negative. Plugging in negative 2, that one is negative. And the denominator is going to be negative 2 squared is positive plus 1 is positive, squared is positive. So, positive. Plugging in 0, that would be negative, and then positive, and then negative in the numerator. And in the denominator, positive. Plugging in 2, that'd be negative, and then positive, and then positive, and the denominator positive. So in the leftmost region, the overall sign, because there's an odd number of negatives, is negative. So we'll write the negative concavity sign. In the middle region, there's an even number of negatives, so that's positive. Write the positive concavity sign. And in the right region, just that one negative. So negative concavity. So now we can answer the question about points of inflection. Because there were no breaks in the domain, and because the first derivative is defined everywhere, that means that there is a tangent everywhere. So everywhere that the concavity changes sign is a point of inflection. So there's a point of inflection at negative 1 and also at 1. And that's the solution.